All right, for 3.6, it's all about transformations. And what I'd like to think about is I'd like to do a few first, and then we'll come back and talk about the definitions of them. Okay. So one that I've always had some young students do in the past at the high school level is think about something like this. So you've got a triangle that's maybe located at these points. Okay, that is you at a triangle. It's at 2, 1. Okay, that's at 2, 1 and 0, 0 and 4, 3, which is hard to visualize, but there's our triangle, whatever, okay? That's a disgusting triangle. Well, you get the picture, I guess, okay? Whatever. So it looks something like this. There. Okay, great. Give or take. Now, what I want to do to this triangle is I'd like to move it, for instance. Okay, I'd like to move it. And so, how could I move it? Well, I could add something to it. For instance, 2, 3, 2, 3, 2, 3. What would that do to it? Well, it would shift. So it would be at 4, 4. It would be at 6, 0. And it would be at 2, 3. And the idea is that it would just move everything to the left, to the right 2, and up 3. So my same triangle would be here, it just would be, shifted up and over like that, right? Pretty sweet. Now, think about this. Could you undo adding this thing to it? Sure, you can subtract it. In other words, could you invert or undo what you just did? Well, of course you can. That makes perfect sense. So that's doable. That's pretty neato. Something else I like to do with my students is like, well, all right, suppose you have this point here, 2, 2, 1, 5, and let's do 0, 0, I guess, because why not? Again, it's just a triangle. That's all I'm talking about, so I'm not going to get too carried away here. Okay. What would happen if you multiplied it by, hypothetically, excuse me, 0.86 about negative a half, and 0.86. That's a good question, Jay. So that's a 2 by, I'm sorry, so obviously this is a 2 by 3, this is a 2 by 2. Can't multiply it this way, but you can bring it out front and multiply it. So I'm going to go ahead and write it that way. What would I get? I don't know. Well, I'm doing something to this triangle, so what did I better get? I better end up with another 2 by 3. And those 2 by 3s would be kind of the same place they are currently. So let's do this. Let's do, try to decide which way I want to do it. Do I want to do it in... Yeah, well... How do I want to do that? Yeah, I'll do it in Desmos, I guess. Desmos.com. Let's go, baby. Bam. So in Desmos, if you didn't know this, you can add a table. Boom. So my points were 0, 0, and what was the other point? 1, 5, and 2, 2. Okay, there's my triangle. It's easy to see that. Boom. Okay, obviously you can connect the dots if you'd like, and it's not important to me right now. What I'd like to do though is I'd like to multiply those guys. So I'm gonna break out. Oops, I'm gonna break out the old calculator here. So I'm gonna do parentheses. Cool. 0.86, comma, negative 0.5, semicolon. 0.5, comma, 0.86 times 0, 0. Well, not 0, 0, 0, 1, 2. Those are my x's. Oops. And then 0, 5, 2. I get these points. So I'm going to put in a new table. And 0, 0. And what did I say? I wasn't paying attention. 1.64 and 4.8. and negative. Oops. All right, and the last one is 0.72, 2.72. Oh, sweet. Oops, that's 272. What? What happened to my triangle, man? It's like he got rotated. Wait, if you draw the line between this red dot and that red dot, and this red dot, which is still a green dot in the red, what angle is that in there, I wonder? Huh. It's almost like it, wait for it, 30 degrees. As it turns out, this matrix is the well-known rotate it by theta degrees. Pay attention to this, though, about the origin. So I rotated it 30 degrees clockwise around the origin. Now, I personally have always taught this in Excel for the students that I deal with at that level. I think it's been kind of cool for them to see, but it's kind of neat too. Plus, you can handle a lot more points a lot faster. But check this out. What's kind of neat about it is you just come in here and give them one of these. You do whatever you want to do. Don't let me tell you what to do. Yeah. So, oops. Wait. What am I doing? Oops. I need to. How about a keyboard? That might help. What I do with them is I come in here and I just go equals cosine of nice. So anyway, I keep hitting that. Then here equals negative sine radians of this fella. Yep. Okay, and here are your points. Let's say your points are 0, 0. And what were my originals? I forgot what I wrote down. 1, 5, and 2, 2. So then, it's simply a matter of taking, knowing I'm going to end up with the 3 by 2, it's going to equals m mult. And then okay, so the next step is very important. You must go Control, Shift, Enter. Bam! And those are your new points. Okay? Same points out on the other page, whatever. Now, what's interesting about this course then is a fella could go, well, oh wait, I changed my mind, 45. Pay attention, this is really 0. Okay? Ooh, I'm going to go negative 180 degrees. Cool. Weird. So lots of cool stuff. By the way, if you go negative 180 degrees or 180 degrees, what have you done? Well, you've had symmetry relative to the origin, yes? So in other words, what was in quadrant 1 is now in quadrant 3, right? And so notice that the x's and y's switched signs. Also notice that it rotated around the origin every time, okay? That is not true if this was not at the origin. Are you with me? If this was not the origin, then this original point here, notice that they all changed. That's because they all changed, they all rotated around the origin. Okay? So if you wanted to rotate around this point 2, 3, one would have to do an in-between step. One would have to do equals this guy minus 2. What are you doing? Minus 2. There you go. And then equals this fella minus 3, but of course you do it to all of them, right? So then you can just click and drag these two cells over. In essence, what you're doing is some linear algebra here, even though you're like, I'm just dragging some crap in Excel. That's right. What have you done? You've shifted stuff over 2 and up 3, and then now it's simply a matter of going, all right, well, this is my new matrix here, so equals m mult. And what am I doing here by doing this? Well, what I'm doing, you see, is I am doing a composition of functions. And that's actually something we're going to talk about tonight in this assignment, is that you can do a composition of functions. So what I did was I shifted it to the origin, I rotated it, and then now I'm going to take equals this guy plus 2, because I'm going to shift it back from whence it came. All right? And then do this. And what you'll see is that now if you were to plot this set of points here, this set of points has been rotated 30 degrees around this point. Because by transferring it back to the origin, we rotated it around that point and we pushed it back from where it came from. Again, notice what I've done there. I've done 3 functions there. It's a composition of 3 functions. By the way, they're all linear transformations, which we'll denote here in a few minutes what that actually means for us. Okay, so it's kind of a fun deal. It's kind of interesting. What would happen? What happens when you multiply by a scalar just for a good time? Well, if you go 0, 0, 0, 0 times 0, let's just say we times everybody by 5. Well, then this is going to be 5. This will be 25. And this will be 10 and 10. And what you'll see is if you zoom out a ways, what you'll see is that you can draw a straight line through here. And what is that line? Well, it should be y equals 5x, I guess. What? And then the other one would be y equals x, because it's still in the line y equals x. And you can see that they're all still on the same line. What are these points? Well, if you go from here to here, there's a triangle. This triangle here is similar to this triangle here. Obviously, this distance is the same distance as there. It's 5 times this distance, yes? It's a piece of cake. What would happen, though, if one of these isn't at 0, 0? What if this isn't at 0, 0? What if it's at negative 1, 1 or something? Well, then that's a whole different kettle of fish, isn't it? Because now when I multiply, I'm going to get negative 5 and 5. And now my triangle has dilated. This is true. It is true. It is dilated. It has gone from being here to out to here, and from here out to here. Notice that they're all 5 times longer, but it's not dilated where one end stayed put. The entire thing has been pushed out. So in other words, if I wanted to hold this, like this little green point right here, this point here, negative 1, 1, this point, if I wanted to hold him still, I would need to move the whole shebang to the origin first, then blow everything up by a matter of 5, and then put it back from where it came. In other words, do a composition of functions. Now, that having been said, to me this is just a very easy and pretty straightforward lesson in terms of that. So we need a few definitions. So definition number 1, what is a linear transformation? Okay, so a linear transformation is simply put as this. It's called a linear transformation, and notice it's from, this is kind of a big deal, it's a transformation T, and it goes from Rn to Rm, is called linear if the transformation of u plus v is equal to the transformation of u plus the transformation of v for all u and v in Rn. And the transformation of c, oops, that's not a c, of c times v is equal to c times the transformation of v for all v in Rn and all scalars c. Okay, that's the definition of it. Okay, so your book does some weird ones. For instance, this guy here is a little strange. So they say, hey, listen, t of x and y is equal to this god-awful thing. You're like, wait, where did they pull this out of? I don't know, dude. They're going from a 2-dimensional space to 3-dimensional space. Is that okay? Well, it's fine by me. So what would happen if you did that? Well, if you had u, the u vector was x1, y1, and the v vector was x2, y2, Well, let's think about this. What would this be? So let's write this way here. Stop it. Stop it. All right. This would be equal to x1 2 x1 minus y1, and then 3x1 plus 4y1. And then, of course, t of v would be equal to x2, y2. So it would be x2, 2x2 minus y2, 3x2 plus 4y2. And so if I add them together, so linear says this plus this, right? Better be the same. Well, let's do that. So x1 plus x2. All right. That's 2x1 minus y1 plus 2x2 minus y2. And then 3x1 plus 4y1 plus 3x2 plus 4y2. And you're like, well, what am I supposed to learn by that? This is what you're supposed to learn from that. x1 plus x2. This is our new variable. So I'm going to have 2x1 plus x2 minus, and then they both have like that, right? And then here you're going to have 3 x1 plus x2 plus 4 y1 plus y2. Ta-da! That just means they're the same. Okay? And then, could you then multiply through by a scalar and see if that all works? Of course you could. If you're multiplying by the same c's, the only difference is you'd end up with a c here. If you multiplied them all by a c, then of course there'd just be c's here, and then there'd be big fat c times the whole thing, and a big fat c times the whole thing, and then of course if you pull that c out, it'd be the same. Okay? Pretty straightforward. So that just is how you show something's linear or not. Okay, that's pretty easy to do there. Inverses are pretty important, right? Can you undo where it came from? Well, some things you can, right? So, for instance, if I add 5 to something, sure, you can do that. What if I said, hey, listen, you've got this function. So you get some v here like this, and you do a transformation of it, and that's equal to the absolute value of x plus y, and then y minus 3 or something. Now, clearly, you can take whatever y value you have, and you can undo this. That's a piece of cake, right? But the x is what's going to cause us a bit of a problem. For instance, suppose I did this. Well, that would be 1 plus 3 is 4, and then 1 minus 3 is, 3 minus 3 is 0. Nice. But guess what? This is the same thing, right? So my question is, if you see this, from which of these did it come? Ooh, yeah, I don't know either. So some things are not going to be invertible. And it goes back to when you talk about functions back in the day, right? Functions back in the day, this thing is a function because it passes the vertical line test. Is its inverse a function? I don't know. It'd have to pass the horizontal line test, right? And so where x squared washed out is that, well, for a value of y equals 1, there was 2 values of x that made that true. It's invertible. It's not invertible, we say, because it doesn't have an inverse that's a function. That's the game. Okay? And so that's going to be something to think about. If you have x squared, if you have absolute values in one of these functions, yeah, it's not going to work. And it's pretty easy to see why it's not going to work, because that obviously is a bit of an issue. Also, I showed you a matrix transformation. I'm going to define a matrix transformation for you. It says this. So we're going to let A be an m by n matrix. Alright. The matrix transformation T of A is such that Rn goes to Rm. Alright, is defined by this. TA of x is equal to A times x. There you go. For x in Rn is a linear transformation. Okay, it's a linear transformation. Okay? And so that's all you gotta do on that deal right there, see? So then it says over here, it just says, for instance, show on one of these problems in your homework here, it says something to the effect of, projects, let's see here, why would I do that? So, talking the matrix P, for instance, that projects a vector onto a line y equals x. Alright. So how do I do that? Project a vector onto y equals x. How in the devil would you do that? Sounds like it's going to be a vector projection. I mean, does that sound reasonable? Feel like it does. So it's probably going to be something along these lines, right? Here's my vector. Okay. My vector better be a what by what? Well, this is a 2 by 2, obviously, when I got cosine theta, negative sine theta, cosine theta. 2 by 2, this had better be a what by who? This had better be a 2 by however many I got here, right? But this is going to be just a 2 by 1. Okay? 2 by 2, 2 by 1, I'm going to get 2 by 1. That's cool. Let's think about that for a minute, though. If I'm going to pull that off, right. So here's my vector, let's say, and I want to project it onto this vector here. How would that work? I feel like, well, let's see. How do we do vector projections? Let's think about that for a minute. A vector projection of A onto B. Okay. Well, if it's on to B, and B is this line here, which is y equals x, that would be like 1, 1, right? That's one way to think of that guy. Right? So if we're projecting onto that, it's going to be 1, 1. And so what needs to go out front out here? Well, it needs to be, it's A dot B. So it'd be, and I'm thinking about this, but I may not do this here. You'd have A dot B. So it'd be A1 times 1 plus B, well, plus B1, or A2 rather, times 1. So it's going to be A1 plus A2 over the magnitude of A, over the magnitude of B squared. So it's over root 2. Nice. And so, yeah, you're like, okay, so I know what I want is I want a vector, yes? Here's my problem. If I write it like this, am I going to get a vector that I want? And the answer is no. I want to end up with a 2 by 1 vector, right? This is going to give me a scalar, which is not what I want at all. So that's gross. What I want is I'd like to be able to have this so that it shows up and I end up with what I'm looking for, which is, that is, I want A1 times 1 over root 2, and then I want A2 1 over root 2. Now, how's that going to work out for me? Well, I think it's going to work out for me if I do this. If I do A1, A2, 0, 0. Okay? Does that work? Well, this times this is just that, and this times that is that. That's right. Okay? Now, it's possible that someone else might come along and go, is there another way to do it? Maybe. Maybe. Let's find out. What if I tried it? Oops. Come back. Oh, no. No, go away. No one likes you. You're a horrible person. All right, now, what if someone else says, well, listen, I want to do it with that cosine and sine routine. Is that going to work? I don't think so. Maybe. But I don't think so. Let's try it. Cosine of 45. Negative sine of 45. Sine of 45. Nope, that's not going to cut it. See, because if you get this times that minus this times that, it's not going to work. So yeah, that's not what you want to do. So in this case here, that's what you're looking for, and that would be that. So then the question is it linear? Okay, is it linear? Again, if it's linear, what should happen? Okay, well, you should be able to do it in either direction, and it should work for any scalars that you have. Would it matter if you multiply this through by c values? Not a bit. It's going to land on the line. It's not a problem. And would it matter what order you did it in or whatever? No, it wouldn't at all. So that's hunky-dory. Couple more that come to mind, and then I think I'm going to leave it at this. What if you had a piece of something over here? Let's a triangle. Triangles are easy. 10, 10, 3, 7, and 3, 10, because why not? If you wanted to rotate it across reflect it across the x-axis here, or the y-axis rather, what would happen to these guys? Well, you would take these guys here. What would happen to them? Well, we know good and well what would happen to them. The x's would turn negative and the y's wouldn't change. Yes? So what I need to do is I need to multiply it by something. And I need to multiply it by this fella, I believe. Check my math. It's negative 1 times 3 plus 0. And then the bottom row would be 10. And so on across the top. And so on like this. Okay? Now you do the same thing. If I want to reflect it across the line y equals x, what has to happen? Well, if I did that, oops, so that's kind of tricky because this 10, 10 is actually on the line, obviously. So it's not going to move. But 10, 10 becomes 10, 10. It doesn't change. 10 and 3, or 3 and 10 become 10 and 3. And 7 and 3 and 7 become 7 and 3. What has happened there? Well, I think you went through and you multiplied it by something along these lines. So 0 times 3 plus 1 times 10. Yep, that's it right there. Piece of cake. So these guys would reflect over and they'd be down somewhere like this. Okay? And that's the game. They are all linear ones that you're talking about for the most part. The only ones that aren't going to be linear, you'll see a few pop up where they're trying to trick you. The dead giveaways is if they have square roots of x in them, or x squared, or absolute values. It's pretty much a dead giveaway that they're not linear. And so it's pretty easy to do. That's a pretty straightforward kind of a deal there. Okay. I do want to do one more thing, I think, and it's over here on the... Maybe I already covered it. Oh yeah. Yep. So T inverse is equal to T inverse. Notice this, the R and N goes to R and N. So let T be such that Rn goes to Rn. Cool. Being invertible, transformation. Then the standard matrix T is an invertible matrix. Okay. So yeah. So the idea is that standard matrix that we talked about is an invertible matrix. That's what that means. So for instance, I showed you this one earlier. Well, whatever. This guy right here. We said this goes from a 2. This goes from a 2 by whatever matrix. From an Rn matrix to an Rn. It goes. Yeah, it's just going to end up in the exact same location. So the idea is if you do this, you can undo this by taking the inverse of this matrix. Okay. And it'll bring you back to where you came from. Okay, this matrix is totally invertible. For instance, the one we just did a minute ago. Okay, flip and switch. If you do this, I can't do the math in my head. I'm getting too tired tonight. So matrix 0.86 comma negative 0.5. Boom. Boom. There's its inverse matrix. You see that? So for instance, let's do this. Let's do clear. So let's take this guy here. Wait, this guy here. Let's lose that inverse part of it. And I'm going to multiply it by this matrix here. So 2, 6, 9, 8. Those are some x values, and then whatever. There's some y values to go with. Boom, here you go. That's the transformation. That's a 30-degree rotation. Now, suppose I were to take, oops, come back, delete that crap. Go up here and get this inverse function. And then multiply it by this guy here. Wow, looky there. I'm back where I started from. Who saw that coming? So it's an invertible function. In other words, you rotate it 30 degrees, you can unrotate it 30 degrees. Okay, that's a nice deal about the linear transformation. Again, the big deal of linear, it really comes down to it's invertible. That's a huge concept of it. I think your book kind of glosses over that a little bit. In terms of things that aren't linear, it's kind of hard to undo them. Okay? Just saying, most of the time that's a true statement. Yep, I think that's all I wanted to talk about tonight. Alright. Anyway, I think you should be okay on that. We are going to have a project this term. One of the parts of this project will be a transformation, some linear transformations of some graphics. So, and it's kind of fun, I think. I'm going to have you do what my